The 32nd lecture on ECD. We will continue studying some useful terms about operational amplifiers. The first term that we will study today is common mode rejection ratio. In the last lecture, we studied about the common mode input. These are the inputs. This is the case where we have applied the same input on both input terminals, but if we apply the same input on both terminals, even then we get some gain, some output. So there is some gain associated with the case where we have exactly two voltages, exactly the same voltage applied on both inputs. And AOL is the open loop gain, that is we get when we have different inputs applied on the two inputs of the operational amplifier, and the output is this times AOL times the difference of the two. So CMRR is defined as the OL, open loop gain, divided by the common mode gain, which is very small. Ideally ACM should be 0. There should be no gain. The output should be 0 when we apply the same voltages on both inputs, but actually it is not. There is some voltage at the output, and the gain we call as ACM, the common mode voltage gain. And the important thing is that it's very small. It's very small. So CMRR can also be represented in dBs. 20 log, since the voltage gain, therefore we multiply it with 20 log. If it would be a power gain, we would multiply it with 10. So now we'll multiply it with 20 to convert it into dBs, decibels. So a small example that we have AOL is 100,000, ACM 0.2, then CMRR comes out to be a very high value, 500,000 or 114 dBs. So larger CMRR is good. Large CMRR is good, means the effect of noise has been better addressed by our op-amp. So larger CMRR means a good operational amplifier, because it is obtained when we have large AOL and small ACM, the common mode gain, which is undesired. Ideally ACM should be 0, so anything divided by 0 should be infinity. The ideal value of CMRR is a good question. It can be a good question in the mid, that what is the ideal value of CMRR? It should be infinity, but actually it is very large. It is not infinity in practical cases. In this example, it comes out to be 500,000 or 114 dB. So the other term that we will study today is common mode input voltage. Is the max common mode input voltage that we can apply on the two inputs, so that there is no clipping at the output. Because if we exceed from this value is generally smaller than the applied voltages that we have applied, the positive and the negative VDC that we apply. It's smaller than this value, plus V and minus V that we apply here. So this voltage is smaller than the value it's given in the data sheet. It's a common mode input voltage. It should be smaller than the supply voltage, so that we don't have any clipping at the output. So it's also a parameter, or it's also a term that we use for operational amplifiers. Input offset voltage is the voltage that we require to apply to the two terminals of the operational amplifier to get the output is equal to 0. We have studied earlier that if we apply a common mode input, then this means that we apply, for example, if we short these two together and apply this one and apply a ground, the output isn't 0. The output isn't equal to 0. It should be equal to 0, but due to a slight mismatch of transistors within this amplifier, the output is not equal to 0. So what we have to do is we have to apply a small difference of voltage. We call it VOS. VOS, offset. It's not output. This O doesn't stand for output. This is off. This S stands for set. So VOS is actually an input voltage that we apply between the two inputs, the positive and the negative terminals, the positive input and the negative input, and then we get V out is equal to 0. The output voltage is equal to 0. So otherwise, if you apply 0 volts on both inputs, the same values on the both input terminals, we don't get the output is equal to 0 practically. Ideally we should get. But to make output is equal to 0, we have to apply an offset voltage VOS that is non-zero, and that will bring your output to 0 volts as desired. Right, so this is the input offset voltage VOS. Then input bias current is the average of the two currents taken by the two input terminals. So it's simple. Input impedance is the impedance that we see when we look into the input terminals. So it can be divided into two parts. Can be a differential input impedance or a common mode input. If differential means that if we look at the whole resistance between these two, this is Z in, and if we apply common mode means if we apply the same input to the both terminals, the input from this input terminal, or if we apply the same input voltage to this end and to this end, to this input and to this input, so the resistance that this input sees with respect to ground is Z in Cm. Cm stands for common mode, and the input seen by this at this input terminal to the ground is also C in Cm. So here we don't apply the same voltages, we apply differential voltages, means different voltages at this positive and negative input terminals. So here we apply different inputs, here we apply the common input. So we can have Z in differential, we see D in differential when we apply different inputs at two input terminals, negative and positive, and we see Z in common mode from each terminal to ground if we apply the common mode input to the op amp. Right, so the last thing for this lecture is input offset current. Input offset current is the difference of the two currents. If we have the same input applied, this is the case when we have same input Cm. If we have the same input applied, then V1 is equal to V2. We apply the same inputs on both input terminal. We should get exactly the same current flowing into the both terminals, but actually it is not. I1, the flowing into the positive terminal, is a bit different from I2 that is flowing into the negative terminal, because there is a slight difference between R ins here. So this difference is I1 minus I2. So VOS, the input offset voltage, can be then written as I1 times R in minus I1 times R in times I1 times R in minus I2 times R in. Why minus? Because this voltage is positive. This voltage is measured such that we apply the red terminal at positive voltage and the black terminal at ground, but here we have the opposite polarity, therefore we put a minus here, this minus. If you would measure it from here to here, we would put red terminal here and black terminal of the voltmeter here, that would also be positive. So here we are measuring a positive voltage with respect to ground, therefore it is negative. So taking R in common becomes I1 minus I2, and magnitude of I1 minus I2 is IOS. So the output voltage, if we have the same input voltage applied to both terminal and there is a mismatch of currents I1 and I2, there is some output voltage, that is AV times IOS times Rn. So AV is the voltage gain. In fact, this is AOL, the open loop gain. This is the difference of the voltage. This is the net voltage that is between the two input terminals. This is multiplied by AOL, and we get this output V out, and that would be non-zero, of course. So that must also be adjusted by applying some offset voltage at the input so that the currents are matched, and we get a zero output when we have exactly same inputs applied to the both input terminals of the op amp. Right, that's all for this lecture. In the next lecture onwards, we will keep on studying more interesting things about operational amplifiers. Thank you.